G'day there, you're watching the Aussie BIM Guru, and today we've reached part 2 of my Sun Hour analysis series using Grasshopper and Rhino. So previously, before this series, I looked at doing this in Revit with Dynamo, obviously a much slower workflow than using Grasshopper, so this is a much more efficient way of analysing your sun. So we've previously run a study on the left that you can see there, and that's pretty much the result we got from part 1. So we had a city context model and a building we were testing. In this part, we're going to focus more on what's on the right, so actually processing our results into something a bit more meaningful, and also refining our study. We used Ladybug previously, so you will need this still in order to run this second part. There's some problems we're going to target in this session. So one is that some of the faces of our study aren't relevant. So when you test a building for sun hours, typically you only really want to test the spaces that are horizontal or relate to a living space, because at the moment we're also testing the top and the bottom of our building, as well as the terraces that occur partway up the building as well, which aren't relevant, so we need to get rid of these results. We're also going to find a way to process our data more meaningfully, because at the moment you just get a really big list of data for each point that's been tested. So we need to make more sense of this so that a basic user can understand what they're seeing. So time to process some data, so let's get started. So we're just going to jump back into Rhino and Grasshopper where we left off. So this is where we reached at the moment. Just to really quickly recap for people that hadn't seen the first part, essentially we've set up a whole bunch of inputs to determine a date range. We've imported a weather file, created the sun path, taken the vectors of the sun, and used a ladybug sunlight and our analysis study in order to process these into what we see here. So essentially all these colors represent the number of hours per sensor mapped onto a grid of a size that we've determined, which in this case is 3 meters by 3 meters. But of course, being Grasshopper, all these inputs are changeable. It's important to note that we've used a BREP to create our building mass, which is a closed poly surface at the moment, and we've used our city as a mesh or a set of meshes, and then that's how we've processed them. We're not baking our results at the moment either, but now we're going to proceed and actually process our data. So the first problem we have, if we just take a point node and feed this into our test points, just to see our test points, you can see that we've got test points occurring on the flat surfaces of our building, which is wrong. So we don't want to have these points as a part of our study. So we need to find out where these points are occurring. So we're going to set up a little script that essentially deconstructs our boundary mesh or our BREP. So we're going to look for a deconstruct node. So we need to deconstruct BREP, and we're going to connect this back to our initial testing mass up here. And this should give us a BREP. We're just going to hide our study for now and just focus on our BREP. So I'll just turn off the preview for these. Sorry, it's my cat. Okay, and I'm just going to make this a hidden wire as well, so it sort of stays out of the way. Okay, so what we need to do now is we need to find the direction the face is pointing and find anything with a Z vector that's parallel to the basic Z. So we're going to get an area, an area node, and the reason I'm taking this is because it also gives me a centroid of faces. So I want to find the center point of each face on my BREP. From here, I'm going to do a evaluate surface. So I'm going to look for evaluate surface, and this is a fantastic node. It gives you a lot of information about a surface at a point. So at the center of each of those faces, I want to find out a bit of information. So one thing that we get that I care about is my normal, which is basically the orientation of the face. This is given as a vector, so we need to deconstruct our vector because I need to analyze the X, Y, and Z components using a formula. So we're going to take our normal vector, deconstruct it into its components, and then we're going to make sure that we're working with absolute values, because if a vector is pointing down, it's negative. If it's pointing up, it's positive. We only care about finding out if it's in the Z direction. Whether it's up or down doesn't matter. So we're going to use absolute in this case. Whoops, I've just locked down my canvas. So it jumped into Rhino there for a second. There we go. So we're going to take a few absolute values for our X, Y, and Z. And we're just using this to figure out if any of our vectors are pointing directly up or directly down. I'm probably doing a bit of an exhaustive method here. There's probably an easier way to determine if vectors are parallel to each other. But in my research, I found that it's not that simple. Most solutions seem to be quite long-winded. Okay, so we're just going to create an expression now to determine this. So we're going to need 3 variables for our expression. So we're going to need x, we're going to need y, and I'm just going to zoom in to get my zoomable user interface, and we'll get z. It knows that I'm looking for z, obviously. So we can have x, y, and z. And my expression will just be a formula that helps me lock in on whether z is 1. So I'm just going to make a formula and say 2 times x plus 2 times y. Looks like it's auto-saving. I probably should change my autosave frequency in Grasshopper. I do find it chugs a little bit too much. 2 times y plus z equals 1. So we're just checking for a boolean. So obviously if we're pointing in an x or a y orientation, this won't equal 1. So we just need to make sure that that's the case, because obviously a unit vector of x or a unit vector of y times 2 will never equal 1. It will always be 2 or a number greater than 1. Okay, so we'll get a whole list of booleans of trues and falses that basically say, is the face pointing a particular way? What we need to do now is use a cull pattern. So anyone that's used Dynamo will know the filter by boolean mask function. In Grasshopper, it essentially works in a function called cull. So we're going to create a cull pattern on our list. So this is our true or false mask, or list as we call it in Grasshopper. And then we're going to exercise that over our faces. And essentially this will give us just the faces that are true. So if I go back and turn off my preview here, you'll see now we're only dealing with our faces in the Z direction. So essentially we've successfully processed this data now. And I'm just turning off a few previews as I go. What we're going to do now is join these, because these are all separate meshes, or trimmed surfaces, I guess, or untrimmed surfaces. But we're going to turn them into meshes and join them using mesh join. You could do brep join as well, I guess. But I find meshes are faster to deal with. I'll just turn off my preview here now. Cool. Sometimes I like to use the middle click menu. It's a bit faster. Okay, so now we've got this as just one big mesh. And what we want to do is we want to find out which points of our test points are almost right on these surfaces, because we want to omit these points. So we're going to use a function called pull point. And this will move a point as close as possible in the shortest distance to a piece of geometry. So our geometry is our mesh, and our points are going to be our test points from our study back here. Okay, so you can see now we've pulled every single point onto these surfaces. Obviously points on these faces would actually have been pulled on here technically. So now we need to find out the distance between these. So we can see the distance that the points have moved here, I believe, straight out of the node that they've moved. So this will help us identify which points are right on the face. So what we need to do now is just double check which ones have moved a smaller distance than a certain tolerance. So we're going to do a small than, or a smaller than, and we're going to check if the distance is smaller than an expression. And we're just going to times our original offset from our test surface times 2. Because obviously we need to be able to get back to the test surface still to find those points, because all our points that we tested have been pushed off the surface by Ladybug. So we're going to get another expression, and this one's a very simple expression. X times 2. Very basic. I'll just take this out and call this X. Okay, so we need to go and take our tolerance from the face of our surface, which is back here, distance from face, times it by 2, and cross-check if these are smaller. And we're going to be checking if they're smaller than, and we're going to be using a dispatch function. So dispatch is similar to cull pattern, except it gives you both the true and the false as 2 separate lists. So it's essentially the same as Dynamo's filter by boolean mask function. It gives you your trues and your falses as an in or an out list. So I've got a cat coming. So we're going to use dispatch. So we're going to exercise a dispatch pattern upon our test points. So I've just got a cat in the way. There we go. So we're going to go back and get our test points again and dispatch them. So I'll show you what this looks like in a second. So okay, so we're going to turn off the preview for our dispatch because we don't want to see all of these things. I'm also going to turn off my pull point and my mesh. So if I just put in a custom preview, we can see that if we feed in this geometry, you'll see that it's found all our test points that are pretty much on our surfaces that are flat. But it's also given us access to our points we care about. So this is how we can basically break our patterns apart. We're just going to keep this over here just as a preview. So just in case we need to see it later on, just to test or validate, we can leave it there. But essentially what we need to do now is dispatch our sunlight hour results instead. So we're going to take this dispatch, and what we'll do is just copy it. And instead, we're going to dispatch our sunlight hours. So sunlight hour result is what we're looking at here. We're going to flatten this as well, because at the moment it's broken, I think, by face. It breaks the results by, or it's by vector. So we want it to just be one big list. So you can see that you get to a certain point and then it resets. Okay. So we're going to take this, and we don't need a flatten list node. We can just go flatten, and our output will be flattened. Looks like it's saving again. Cool. All right. So we'll take these sunlight results as a flattened list and connect this into our dispatch pattern. And essentially this will dispatch our results into the ones we care about and the ones we don't. So you can see now we've sort of omitted a lot of our results that aren't important. So that's great. Okay, so what we need to do now is with our dispatch results, we will round them. So I believe at the moment these have decimal values included in them. Sorry, I keep getting the wrong node. So some of these will be things like 2.5, 1.5, etc. In my city of Sydney, you can only count hours if they're full hours of sun. You can't say 2.5 hours. You just have to say we've got 2 hours of total, and the half hour doesn't count. So we're going to use a round node just to round this down. I really like the round node in Grasshopper because it gives you a few options in one. It gives you nearest, your floor, which is your round up, or ceiling, which is your round down, which is brilliant. So obviously we care about our floor in this case. So one thing we can do straight away is get a graph, just a bar graph, and we can feed in our floor. And straight away we can see roughly or visually our results as a percentage. So we can see that, you know, we have a decent amount of hours between 1, 2, 3, 4, 5, 6. Sometimes the scale I find can be a little bit awkward in these. The scale really depends on just how big you make your graph. But certain scales seem to work better than others. You can see 0, 1, 2, 3, 4, 5, 6, 7. So it doesn't scale properly to the results. I think there's a way to set that. So you say I want 6 bars. And there you go, 6, 5, 4, 3, 2, 1, 0. So we actually want 7 bars. So if you set the right number of bars, there you go. So now we can see roughly the number and the rough percentage of each result. But we might want to build an explicit list of exactly what percentage of hours we're getting for each result. So we might want to know which percentage of the surfaces are giving us 2 hours or more. So what we're going to do now is process these numbers. So the first thing we're going to do is sort our list. So we're going to sort our floors as keys. And then from there, we're going to create sets. So essentially this will break up our data into sets of numbers. So we can count the size of our sets. I believe we need to use a member index here, that's right. So this part's a little bit complicated. I had to go on the internet to sort of figure some of this out. So you might just need to bear with me here in terms of how this works. I've sort of had to replicate another workflow someone shared for a different purpose. But I think what we get now is we get a bunch of indexes and counts of how many of these. So we get all our indexes of our results. And then we get counts of all of those as well. I'll just have to cross-check this is working. It looks a little bit like it's not working at the moment. Just have to cross-check that this is all coming through as a flattened list. It's a flattened list. Yeah, I believe I've used the right workflow. This is how it works for me before. It looks like everything's still coming through as sublists though, so that's a bit strange. I might just try out putting a flattened list here, just to see if that changes my data. Okay, this looks better. I think this is what we expect. There we go. This is what we wanted to get. So we basically wanted to find out how many occurrences of each result there are in our data. So the way we've done that is we've created sets out of our data. So we found the number of types of values that occur in our list, and then we've had to count how many of those occur as a member. So there you go. Now we can see this is the number of results, but we want to turn this into a percentage. So thanks for bearing with me if you got a bit lost at that bit. So we need to use mass addition now. So that basically just creates a sum of each of these. So this is going to give us the result of how many hours we have in total. So we have 22,000 sensors, and then we know how many results we have per hour count. So now we can find the percentage of these. So we can do a division node. Division, and we can divide each of these by the total. And then with this, we can also round. So at the moment, we have all of these values. We're going to round, but we're also going to apply an expression. So obviously, if we round here, we're only going to get 0 or 1. But I can nest an expression in here. So I can say x times 100. And then this will actually feed these in as a formula. So these already get multiplied by 100 just by being connected to this node. And then from here, we can take our nearest as a whole percentage. What we need to do now is actually evaluate these using an expression in order to make them read in a particular way. So we're going to use the evaluate node in order to create a text expression. So we're going to create variable, well, we're going to create x, and we'll just create y, and we're basically going to use this to process our results, but we're going to have to write out an expression. So x in this case will be our set. So our set is essentially our result, so 0, 1, 2, 3, 4, 5, or 6. So that's our first variable, and our second variable is our percentage. And what we need to do with these is feed in an expression, and we can just use a panel to write this expression. So we're going to write out a text format. So we're going to specify a format bracket, and we're going to create an apostrophe and colon our first index as hours, and then we're going to call on our other index, and then specify our variables that fill the place of each of these strings. So essentially we're setting up a basic text formatting formula. So essentially it will say the percentage of hours per the result with percent. So 0 hours, for example, x percent. So 2 is percent, y is the second variable, or the first variable, I guess, and the index of 0 is going to be our hour itself. So if we feed that in, this should evaluate into a bunch of sentences. And you can see we've got 0 hours, 34%, etc. And from there, you can just connect this up to a panel. And you can see your results as percentages. So that's great. So essentially, we've really created some data that a user can analyze now. So I can actually go hidden on this and move this, somewhere a bit closer to the bar graph so that we can see these results alongside the graph, so that it all really makes sense. And I've noticed a lot of Ladybug tutorials don't really touch on this part of the script where you need to actually make your results mean something. So hopefully this helps people actually analyze their results more effectively, because I found that this was critical to the way that the script needs to be run. Otherwise you really can't make sense of what Ladybug's telling you. So obviously once you're done, you can go back and turn on your study, and also turn on your city mesh. And there you go. But in the background, obviously all this stuff is also now occurring when you run the study. So that's great. And also you can always turn on your custom preview for your omitted results too, if you ever need to see them again. There you go. And also you can pick your omitted ones instead. There you go. So so hopefully you find that helpful, and hopefully that sort of helps you round off a sun hour study in Ladybug with results that you can actually use to inform your design decisions. So thanks for watching the series. I've used Rhino 5, I forgot to say that, so I'm not using Rhino 6. And I got started, so missed a couple of slides there. Anyway, so thanks for watching today. Hopefully that helps you undertake a study. I look forward to sharing more Grasshopper related workflows with you in future. If you have any suggestions or feedback, feel free to leave it down below. And if you're not already following and subscribing, feel free to do so. Thanks for watching, and I'll see you in the next video. Take care. Bye.